Any 7.2 questions? Want me to just pick one? 44. All right. One of the things about 34 or 44? Okay. Oh, 7.1, 44. Okay. Okay, so whenever you're asked questions about the hypothesis statement, making a hypothesis, you want to construct in words and symbols what the question is referring to. And that's the first step in the 3-step process. Step number 1. Okay, and typically we're going to ask a question and then you need to answer it using statistics. You can't just use your opinion, right? Most people use their opinions, especially when you're online on social media and stuff like that. A lot of people and news personalities and stuff use opinions about certain things or certain topics, but data is what we want. We want information about what's going on in the world, and especially in things that are political, right? You want to use data to make determinations about things that are happening. So in this question, it says a government agency claims that more than 75% of full-time workers earn over $538 a week. This one's a little tricky because they gave us two things. They gave us a proportion and they gave us a mean. So we really have to target what they're asking for. Okay, so I got to write the hypothesis. So the claim is usually what your hypothesis is going to be. A government agency claims that more than 75%, more than, there, I heard the words. We have 3 hypothesis statements that we can make. And this page is one that I'm going to refer to quite a bit. Page 349 has the hypothesis on there. So if you want to refer to page 349, we're going to look for the words more than. What does more than mean? That tells us greater than. Okay. So there's really 2 choices. We could do a greater than equals as the HO, or you do a greater than as the HA. So we have to determine which is which. So if I go to page 349, it's pretty much a template to help us determine which one to use. So I'm just going to look for the words more than. And I see more than K on the right side, second box. Page 349. So it says use mu is less than or equal to K, or mu is greater than K. So there's my hypothesis. More than 75% make over $500 a week. So I'm going to write it now in symbols. So that's words. I'm going to write it in symbols. Again, this is 7.1, number 44. So am I talking about a population mean or a population proportion? One of the things we're going to get to today, these things all involve means. This is pretty much 7.2. This is 7.3, what we're going to do today. But 7.4, we're going to talk about proportions, comparing 2 proportions. So in this case, I'm going to write it as a P and not a mu. And it says more than. Okay, one thing I did not mention yesterday was your equals, your equality statement is always going to be on your HO. And traditionally, I like to write them above each other and below each other because that's how the book does it. You could write them side by side. It's funny because the book, in our textbook, they author it to have HO on top, HA on bottom. But then when you read the examples, they put HO and HA side by side, which is kind of funny. So I like to stay streamlined and be consistent. So I'm going to write more than is going to go on the bottom. So there's our hypothesis statement. Now in the question, it doesn't ask us to do that, but that's something that we want to measure first based on this information. Determine whether the claim represents the null hypothesis or alternative hypothesis. If a hypothesis test is performed, how should you interpret the decision? So what's the claim? It says the claim is that more than 75% of the population earns over $500 a week. So we're gonna write the claim is either HO or it's HA. So it said more than, there's the claim, so I'm gonna say that the claim is the HA. And usually we just put parentheses, claim. That's what they told us, right? And we're gonna collect data in 7.2 and compare our data to what our claim is going to be. One of the things that you'll see in other textbooks or in other classes, some teachers teach it a certain way. They'll just put an equal sign here in your HO. Your HO is always going to have an equal sign because our measurement is comparing 75% to some value from sample data. Okay, so HO being less than 75% is pretty unlikely. That's why they usually use equals. When you get more into testing and you're doing the normal distribution, it'll make a little bit more sense, what I just mentioned, but for right now, we're just gonna write it that way. So what's it mean to reject the null hypothesis? So in step A, what does reject mean? In words. So if I reject HO, remember I gave this yesterday, if you reject, that means there's evidence to support. I don't like to say support the claim. I would say if I reject this one, it's not this one, it's the other one. Okay, so what does that say? That says there's evidence that more than 75% of people make over $538 a week. So reject HO, I'm gonna write it, I'm gonna take it in symbols, now I'm gonna translate it to words. There's evidence. Whenever you reject, you would say there is evidence. More than 75% earn over $536 per week. I left out the word full-time worker. It said full-time worker on there. What does it mean to fail to reject? And that's kind of like what it was talking about, the type 1 and type 2 error. If you fail to reject, that's like making, like you said, type 2 error. That's what you said, right? Rita?
No.
Oh, exactly. Thank you. So she said that means there's not enough evidence of HA. So either we say there is evidence when we reject, or there's not enough evidence. I don't like to say reject a claim. Okay, and I had this debate with a statistician that was way smarter than me, and he's an author of several textbooks, and he said, he put his foot down, he's like, you cannot reject claims. You can only reject the null hypothesis. Okay, because sometimes the claim will be your HO. Sometimes this is the claim, and there's a couple problems where the claim is the null hypothesis. So we don't ever reject claims, we always reject HO or fail to reject HO. Okay, so fail to reject HO, does that mean there's not enough evidence of HA? Okay, so if you reject, say it's one or the other. It's like a true false, like a left, right, up, down. There's only one or the other. We are going to conclude based on data, and we'll get to a lot of this today. Based on the data, is the answer HA or is it not HA? Okay. We don't want to use the words, oh, HA is true, because it's only based on a sample. We could make it a type 1 or type 2 error. Okay. We don't know if things are true or not. We just have evidence of something. We also don't want to use the words accept. Okay, I don't accept the HO. I could say if it's not this one, it's that one. Or I could say, oh, it's HO. It's kind of a one or the other. Okay, in most cases. And again, this is just 7.1. We're just preparing you for 7.2, where we're going to do a Z test and a T test. All right, so that was 44 hourly wages. There's lawnmowers, gas mileage, healthcare visits, calories, swans. There's nothing in here about cholesterol. I just got a doctor's appointment today, telehealth. I did a FaceTime with my doctor and said, oh, your cholesterol is a little high. The max is 180. You were like 184. I was like, oh, that's terrible. Terrible news. I've started exercising. I haven't exercised in a while. It's been a while. Time to start not eating fast food, right? Fried food, all that good stuff. All things in moderation, though. That's the key. I heard an interview with it was like on Dateline or something. They got a bunch of 100-year-old people in a room, and they said, what's the secret to long life? Because that's what everybody wants to know, right? What's the secret? And they pretty much said all things in moderation was the conclusion that I got from watching this interview, based on, it's qualitative data, it's their opinions pretty much. But one of the gentlemen that was on there, he's like, yeah, my kids made me quit smoking when I was 90 and quit drinking when I was 100. It was like 104 or something like that. And he said he never did too much of it, though. He never exercised too much. He never drank too much, he just like once in a while, just whenever, wasn't his thing. He just smoked cigars or something like that. And he's like, yeah, he was too old for that stuff. He said he never he exercised, but never like a regular, he was not a health nut, he wasn't like working out a lot, and I spent a lot of time in my life working out and being fit. I ran a couple marathons, and I came to the conclusion after running a marathon, it's like, that's like the dumbest thing in the world, running 26 miles, and I did it twice. It's just really bad for your body. It's really unhealthy and bad. My bones were hurting all the time. I was like, this isn't a way to live, just like always in pain. And it was from running too far, right on the street. It's terrible for your body. Half marathons, I don't know, 13 miles, that's still pretty far. But cholesterol, I just got on a tangent there on cholesterol. Cholesterol, they got an average cholesterol, a max cholesterol, I think 180, LDL, HDL. So those are things that are measured based on data collection over long periods of time. We could do a sample test to compare where your value is compared to all values, or take a sample mean, take a mean value and compare it to all values. So we're taking a sample mean right here and comparing it to a population mean, and use that population mean value is typically your parameter that's claimed. There's healthcare visits, there's calories, security alarms, clocks, golf, lung cancer. So data that's been collected long periods of time. We have information that's grown over time to make decisions. Any other 7.1? Okay, how about 7.2? Okay, something came up. I'm not sure if you've been reading the textbook, but that's one of my secrets to success, is to read the book. Actually, it's more like science class. There's a lot of reading in there. If you ever are having trouble sleeping at night, and insomnia or whatever, a lot lot of people suffer from that or sleep apnea. You can read our textbook and put you to sleep, right? But there's a section in here about rejection decisions. So rejection decisions are based on rejection region. I put right over here in the second step in the calculations. This is where we got into z-score and p-value. So if you can calculate the p-value from the z-score, that'll allow you to make a rejection decision. And it's one of the most important things that we do is making that decision. Rejection decision based on the p-value. Well, we can base our rejection decision on a rejection region. Okay, again, this is a summer class, and I usually in the fall class, I spend time with rejection regions and talk about it because it paints a picture. A lot of people say they're visual learners. I need pictures, and the pictures will help explain it. And so that's where I draw the normal distribution curve. And you'll see that in all the examples, and all the examples, they go through finding a rejection region and the Z critical value, or in this case, what we're going to do today, the T critical value to make a rejection decision. I'm just going to talk a little bit about it today. I'm not going to try to confuse you, but it's in the book, and the examples take you through those things. Okay, so I want to try to clear that up a little bit. Nobody's online, got questions? All right, we're ready to go. Rock and roll. So 7.3, I already got the notes on the board for 7.3 right here. 7.3, we're going to do t-testing. So I want to give you a few notes about what it means to do a t-test. There are guidelines on page 377. So 7.3, that's a 7. T-test. How do you know if you're going to do a z-test or a t-test? It's the same as a z-interval or a t-interval. You're going to be given standard deviation. It's kind of tricky in the wording of the question. The wording of the question will say, given a sample of 50 people, we found a population standard deviation to be 1 ounce for filling bottles of soda. Okay, so the population standard deviation is usually a given, and it'll say that. If it's a sample standard deviation, typically it won't say sample standard deviation. It'll just say standard deviation. And the standard deviation is going to come from the sample. In a sample of 20 students at Hancock College, we found the average GPA to be 3.0 with a standard deviation of 0.2. That standard deviation comes from the sample of 20 students. It does not come from the population. So you got to really read the words, and this is what you're going to see in t-testing for 7.3. We have this thing pop up again called degrees of freedom. So we're going to use the t-table. We can use the t-table, but we don't have to. T-testing, we can do it on the calculator. We can do a t-test on the calculator, but I'll take you how to do it by hand, and then we'll do it on the calculator for several cases. So finding this T critical value is pretty important. And on the last test, I believe we had to find T critical values, right? So that's where you're given a sample size, 35 people. If we have 35 people, that means 34 degrees of freedom. We subtract 1. If it's a 95% confidence, then we go to that value, 31, 95% confidence, the T critical value. Okay, so we're going to use the T table. I'm going to look at the T table real quick because there's going to be a little difference between what we do in intervals and what we do in testing. Finding this T critical value. So again, it's in the back of the textbook, or you can Google if you're on your laptops. I see a few people. You can Google T table, right, and have it bookmarked or whatever. Table 5, T distribution table. So hopefully you're taking a look at it. Can't really share it on. I could share it on the projector, but I'm zooming right now. Makes things a little difficult. So table 5, A18. So I mentioned if n equals 32 and 95% confidence, what is that T critical value? Okay. So I'm going to just go down here. We're just going to get familiar with the table once again. N is 32, so I don't go down to 32. I actually go down to the number 31. So with n equals 32, that means there's 31 degrees of freedom. We subtract 1. So I go down to 31, and I go across to 95% confidence, and I see 2.080. So it's always around 2. About 2 deviations is considered unusual. That's our cutoff. That's where we say anything above 2 is going to be unusual. Okay, so 2, 1.96, 2.08. Okay, it's always going to be a number close to 2. Okay, we're getting down to, you know, what they call it, splitting hairs is an old saying that is used. I mean, that's really close to 2. So that's for a confidence interval for a T interval. I'm going to talk about now alpha level. That means DF is 31. What is our T critical value?
I think the T critical value for the top is 2.04.
Did I look at the wrong one? 2.04. Thank you. Where did I find 2.08 at? I don't even know. Oh, I looked at 21. Thank you. 2.040. Thank you. Everybody's looking at me like I'm crazy. Nobody said anything. All right. 2.040. Thank you. I used 21. If you looked at 21, you see 2.08. 2.04. Okay. When n is 32 and we have alpha significance level of 0.05 with 31 degrees freedom, what is our T critical value? Okay, well, this is a little bit different. At the very top is your level of confidence. We'll see the level of confidence directly connected to the alpha significance level. A 95% confidence level is equal to a 2-tail alpha. So we have to really come up and decide, is this a 1-tail alpha or a 2-tail alpha? So I got to explain that. If this is 2 tails, we use the same exact value, 2.040. Do you see that line on there in table 5 where it says 1 tail and it says 2 tails? 95%. I have to draw a curve now. So the middle 95%. If from here to here is 95% of your data, then left over in tails is 5%. So right over here is 5%. And here combined is 5%. So that makes this 2.5% and this 2.5% combined. That makes 100% of your data. So typically for a 95% confidence level, we'll use an alpha of 0.05. It's the same. If you look at a 2-tail alpha, 0.05 gives us 2.040. But what if it's 1-tail alpha? Notice that the column shifts over. If you're doing a 1-tail alpha, so this is for 2 tails. If you're doing a 1-tail alpha, you would use a different number. So let me draw this picture. So using the last example, we thought that more than 95%, we're going back to the previous, more than, or is 75%. And our HA was mu, or I'm sorry, not mu, P is greater than 0.75. What I'm gonna do, it says greater than, what's the probability of being greater than 0.75? I gotta draw this really small. So I'm gonna do a 0.05, so now I'm gonna say if 0.75 is in the middle. This area is 0.05. That's a one tail alpha. So if n equals 32. And alpha equals 0.05. That means there's 31 degrees of freedom. T critical value for a one tail alpha is going to be a little bit different. So for this T critical value, we would use for two tail 2.04. Well, that's not going to be 2.04. Okay, this area is twice as big as that area. So the number is going to be a little bit smaller. So if I go to 31 degrees of freedom, I go to one tail alpha 0.05, and I see 1.696. That T critical value is now 1.696. So this is just finding T critical values based on if you're doing a left tail test, a right tail test, or a two tail test. Each one is different. How do you know which one is which? This says greater than, called a right tail test or a one tail. If this says less than, I'm finding areas over here. If it says equals and not equals, then I do a two tail test. That's where we use 2.04. And notice the difference, 1.696, 2.04. Now there's a big difference between those two numbers that we're going to use. So finding T critical values, we could use the table. We'd also use inverse T. Now I recognize that not every calculator has inverse T, especially the TI-83. Are there any TI-83s out there? They're kind of disappearing. I don't think TI-83s are being used very often anymore. So everybody has inverse T on the calculator. If you go to your calculator, go to second bars under distribution. We're gonna find these values. Where do they come from? If I do inverse T, I'm gonna put in the area and the degrees of freedom. Let me move this over slightly. So what's the area? The area is always a left tail area. I'm going to go ahead and do this first one. When n is 32, that means there's 31 degrees of freedom. That's all we need to know. With 95% confidence, how did I get a T critical value of 0.04? Well, I have to find the area to the left of 2.04. So this area is actually 0.975. 0.975. If I do inverse T, 0.975, and put in 31 degrees of freedom, I should get 2.04. If I do inverse T, 0.025, on 31, that'll give me a negative 2.04, but notice the T critical values in the table, they're all positive. We don't use negative T critical values. We only use positive T critical values. So again, that's where we can use calculator to get all the values in the table. Let's try this one with calculator. And doing all this stuff, this inverse T stuff, it's important, but it's not something I'm going to test you on finding the T critical value. I think there was one question on the last test. Main thing I want you to be able to do is to do a T test. Okay, that's going to be the big picture thing that we need to be able to do. This is just getting there. This is a on the road to finding the solution. So if I do this one, inverse T, I'm going, the left tail area is going to be 0.95 now. from the area from here to the left is 0.95. The area to the right is 0.05. I'll put 0.95 in there. And that'll give me the 1.696. The inverse T 1.696. All right, cool. We got T critical values. I'm going to use that today. We're going to use T critical value today. I'm going to do this statistical test with a Snickers candy bar. I'm going to weigh them, unless you didn't bring one. We got watermelon, we got ice drink, we got Starbucks. Anybody bring a Snickers candy bar? Oh, we got one. All right. A regular Snickers candy bar. So the plan is to weigh as many as we can. The idea is to say, are they giving us what they claim? Have you ever bought a bag of chips and you open it and it's like all air?
Yeah.
And there's like 3 chips in there and they're like, oh, that was 99 cents for that bag. And the price keeps going up and it seems like there's less and less in the bag of chips. Are they giving us what they claim? On the side of the bag, it says 2 ounces. Are there really 2 ounces of chips in there? You can weigh a sample of bags of chips and make that determination. You could do this with any food product. And in fact, I had a student do this. The student was like, I love yogurt. And took yogurt and bought a bunch of yogurts. And you'll plate yogurt on the side, it said 4.2 ounces. He took all the yogurts and weighed all or measured all the ounces in all the yogurts to see if he was getting what they claimed. Because is it exactly in the bag or in the yogurt or in the Snickers candy wrapper? Is it exactly what they tell us? Probably not. So we're going to write a hypothesis. We're going to make a claim right now for Snickers candy bars. Okay. The only issue we're going to have is that we have a really small sample because not too many people brought Snickers candy bars, but that's okay. So I'm going to write a hypothesis. Oh, what happened to that one? It was right in green. So we're going to write this in words and symbols. Do Snickers candy bars weigh? And they tell us how much they weigh. It says on the side of the package. Snickers candy bars, the regular Snickers candy bars used to weigh 62 grams. Then it went down to 58 grams. Now it's down to 52 grams. They've been decreasing the weight of the candy bar and at the same time increase the price. Okay. So consumers don't know that, right? If you learn anything from this class, you'll learn about Snickers candy bars. That's what you'll tell everybody in about 10 years from now. What'd you learn in stats? Learn candy bars. They're giving us what they claim. Okay, what do you guys think? Do you think that when we weigh these candy bars, are they going to weigh more than what they say on the side? Are they going to weigh less than what it says on the side, or is it going to be equal?
Less.
Okay, everyone's saying less. Okay, so that's our claim right here. Do Snickers candy bar weigh less? I want to capitalize it. Then, and on the side it says 52.7 grams. So there's our claim, because that's what we think, right? And that's where claims come from. Same thing with if you get a loaf of bread, okay? If you get any kind of product, a can of soda, a water bottle, it says 16. You ever buy a case of water and look at the water levels, or is that just me? I got a case of waters, and all the waters are different levels, right? Because they take a machine and fill the bottle, and then next one comes along and they fill the bottle. Next one comes along, they fill the bottle. They're all different heights, level heights. So next time you buy a case of water, you can check it. 16.9 fluid ounces. Is there really 16.9 fluid ounces in that water bottle? That's something that we can measure. Okay, and we're doing this with candy bars. I'm gonna write my hypothesis. The population mean is less than or equal, or I'm sorry, greater than or equals to 52.7. I'm gonna draw a picture here in a sec. That's a G for grams. Divide the board up a little bit. Okay. So what are we doing? We wrote the hypothesis in words and symbols. Where did this come from? We have the word less than. Less than is our alternative hypothesis, and that's our claim. Because that's what the question is being asked. If I thought they gave us more than what it says, then I would do a greater than. I would do a right tail test. Step 2, calculations. Now this is where all the information comes. So we're going to find the mean weight. So I got to find the sample mean. I want to find the sample standard deviation. I'm going to find the sample size. I'm going to get degrees of freedom. I'm going to calculate a, now we're going to do a t-test. If I do a z-test, that means I know the standard deviation for all candy bars. I've looked it up online and I can't find standard deviation for the weight of all candy bars. Maybe it's some kind of secret Snickers has, but all we have is sample data based on how much the candy bars weigh. So now it's time to collect data. So I'm going to put the data over here. So let's weigh them. If you can bring your candy bar up and weigh it and then just shout out how much your candy bar weighs. And then after that, you get to eat it, or you deliver it to somebody that doesn't have one. Homeless person, teacher. 55. Some candy bars will make way more, some might weigh less.
54.
You. Oh, you got a king size. Oh, that one's too big. You got a king size as well? Maybe we'll do king size later. Yeah, so you got two. You got king size as well? Okay. Yeah, we'll do a king size. We'll do this with king size candy bars. Okay. Bless you. Oh, you got the monster. Look at that. Did you know that when you bought it, that you're gonna have the biggest candy bar in the class? No. 56 grams right there. Any others? Anybody weighing their candy bar online right now? No? Not too good. Okay, so we got sample size 4. Really small sample. Their margin of error is going to be much greater with small samples. That was one of the properties of the central limit theorem. When you have small samples, greater margin of error. Okay. Standard deviation will probably be a lot different than if you had a large sample. So that's all we have. I got 53, 54, 55, 56. Okay, the mean, I'm pretty sure is right now, it's going to be halfway between 54 and 55, like 54.5 grams. That's going to be the mean weight. Standard deviation, I can calculate standard deviation by hand. I don't have to because we have a nice little tool right here, technology. And if you're working in the field of statistics, you get to use calculators. You don't have to do it by hand. So I'm going to enter the data into a list. I'm just going to use list 1 here. That makes things a little easier. I'm going to enter 54, 55, 56, 57. How do we get our statistics? I'm going to do one variable stats for list 1. How did I do that wrong? I wrote the wrong numbers. So we're going to calculate one variable stats for list 1. And the standard deviation is S 1.29. And it's 4, BF is 3. Okay, so what does a t-test do? It compares this number and that number. Bless you. Okay, the calculation that we do, this t calculation, tells us whether or not is 54.5 is the sample mean less than the population mean. Is this number smaller than that number? Okay, I'll draw a picture. Maybe I confuse you with the words. Okay, so 52.7 is the population mean. We put U in the middle. And we think that the candy bars they give us what's inside that package. Candy bar is going to be less than what they claim. Okay, so less than is over here. We're going to do this at alpha equals 0.05. So I'm going to find this area over here. So what I'm trying to do is figure out is 54.5 less than 52.7. Where's 54? If this is the x-axis, where's 54 at? To the left or to the right? To the right. So 54.5 is like way over here somewhere. Is that less? Okay, anything that's in the shaded region is going to be less than 52.7. So let's say we weighed the candy bars and they weighed 52.6 grams. Well, that's less than 52.7. Is it significantly less? What about 52? What about 51? Okay, so anything over here is far less than 52.7. What is that T critical value? So this is the mean. This is a T equals 0 right here. This T critical value, it's going to be a negative T. I'm going to use my table. So I got 3 degrees of freedom. I got an alpha is 0.05. This is a 1-tail. So I go to 3 degrees of freedom. 1-tail alpha 0.05, 2.353. 2.353. Okay, so I mentioned earlier I was going to talk about the rejection region. Any T, I'm going to calculate T in a second. So T calculation, I'm going to calculate T. Any T over here, far less than that, is going to be negative, less than. Okay. Any T in this region is going to be in the fail to reject region. So we actually call this area that I shaded the rejection region. Okay. So let's calculate the T. 54.5 minus population mean 52.7. Sample standard deviation 1.29. Square root of 4. This will give me my T statistic. This is called a T statistic when we calculate it. This is called a T critical value. Calculations, calculator. I typically will calculate the denominator first. 1.29 divided. $2.79. So this T critical value is 2.353. When I calculated the T for 54.5, I got 2.79. That's way over there. So now we're going to measure the P value. The P value is the probability of finding a value that small or smaller. Okay, because we're talking less than. If I'm talking less than, I'm going to find the area to the left of 2.79. But this is a T statistic. So we'd have to use a function called TCDF in our calculator. But again, I would avoid that because it might cause a little confusion. Oh, it's another formula to come up with. It's another calculation, calculating p-value. The great thing is that our calculator will calculate the p-value by doing a t-test on the calculator. We have the data in list 1. So let's go ahead and go straight to it. Let's do a t-test. To get this p-value. Stat. Test. Hey, number 2 is a t-test. Last time we met, we did a z-test, which was number 1. Now we're on t-test. And why t-test? Because standard deviation came from the candy bars that we weighed, not from a population value. First question in t-test, it says data or stats. We have data. There's the data. We have the weights of the candy bars. Population mean 52.7. That's mu 0. Where's your data? List 1. Frequency, always keep your frequency at 1 unless you're talking like thousands of dollars, like salaries and stuff like that, or home prices. You can set the frequency at thousands if you want to. We usually leave it at 1. Then my third question is not equals, less than, or greater than. Okay, I have a less than. Why do I have a less than? Because that is our hypothesis. That's our claim. So I choose less than, then calculate. Oh, t equals 2.78854. I rounded it to 2.79 because our t table gives us in the hundredths of the decimal place. P is 0.96. P value equals 0.96. So we got our t calculation 2.79, our p value is 0.96. We're ready for step 3. Anybody get confused where I did t-test on the calculator and got a p-value of 0.96? Does everybody see that? Anybody get 0.04? If you got 0.04, that means you did a right tail test. That means you choose greater. 0.08, that means you did a not equals. Okay, the last question, you're going to choose your hypothesis.
For the t-test, what did you put under the mean?
52.7.
Okay.
Mu 0. Okay, that's population mean. So what's that 0.96? The meaning of 0.96? This is the probability that 54.5 is less than 52.7. Okay, 0.96. The area to the left of 54.9, or I'm sorry, 54.5 is 0.96. The area under this curve, that's 96% of the area. So I'm going to use this analogy like the weather. There's a 96% chance of rain tomorrow. That's pretty likely to happen, right? 96% chance of rain. The less likely something is to happen, that's the likelihood that there's a difference. Okay. It's kind of like a reverse proof. It's kind of hard to wrap your brain around a little bit. That measuring the p-value, the probability of finding a value that small or smaller. Okay. So 0.96, 96%. That's a high likelihood that there's not a difference between these two numbers. Smaller the p-value, the more likelihood that there is a difference between these two values, these two means. Population mean and this sample mean. Okay. Is 54.5 less than 52.7? Not really. It's greater than. Pretty obvious it's greater. Okay, we're ready for the conclusion. The conclusion, you're going to be asked for the rejection decision. Are we going to reject or fail to reject? Well, how do we know? In our rejection decision, I'm going to give you a page number. I gave you a page number for your hypothesis. And we looked at this previously. How do we know if we're going to reject or not? And this is going to come up. Page 363. So rejection decision is based on page to put it, I don't know where to put it. Page 363. And what's it say? At the top, decision rule. Okay, your decision rule, the why do you reject or fail to reject? If your p-value is less than alpha, reject. If p-value less than alpha, reject. P-value greater than alpha, fail to reject. What if your p-value is equals 0.05? That hardly ever happens where you have it equals, but if you have it equals 0.05, if the p-value is 0.05, we would still reject. Okay, it's just telling us we got to draw the line somewhere. So what's alpha? Most of the time, this alpha is going to be, and I use 0.05. Most of the time, that's the most common alpha significance level. Okay. Most common alpha significance level is 0.05. So I think I wrote it last time because it was introduction to this. I gave you the p-value was 0.05. And the alpha significance level was 0.05. Could be 0.01, could be 0.1, and those are given in the t table. Okay, those t critical values. So here we are, we're ready for the conclusion. So I'm going to say fail to reject. Okay, why did I say fail to reject? Why? Which one is it? Is the p-value less than 0.05 or is the p-value greater than 0.05? So in part 2, we can have a p-value. We can say what the p-value is, but I already wrote it down right here. There's p-value. I don't need to write it again. I already wrote it. Okay. The p-value is greater than 0.05. 0.96. That's bigger. Finally, we're going to answer the question. What's the question? Question is up there where the hypothesis was at. Do Snickers candy bars weigh less than 52.7 grams? If they do, then I would reject HO and I would say, oh, it's this one. Well, I couldn't reject. Well, I failed to reject. When you fail to reject, there is not enough evidence. There is not enough evidence. Candy bars weigh less than 52.7 grams. That was a lot of work for something we could have concluded right after we weighed them. They all weighed a lot more than 52.7. They weighed, one candy bar weighed 56 grams. I was like, oh, you got the monster, right? 56 grams. I got one that does not weigh less than 52. They'll weigh, all of them weigh more than that. And I would venture out, I only got 4 candy bars. What if we got 4 more or 10 more or 100 more candy bars? I'm pretty sure they would weigh more than that, 52.7, right? And the reason why is the company does not want to get sued for something like this. Companies have been sued, consumer reports, consumer advocate groups. They live for things like this, right? So there was Star-Kissed tuna. They were putting less than 2.2 ounces of tuna in their tuna cans, and some consumer advocate group got a bunch of Star-Kissed tuna and found that what they were putting on the side of their can of tuna was wrong. They were giving us less than what they claimed. They did a statistical study just like this, and you're entitled to 10 free cans of tuna. I'm sure it's expired by now, but somebody's sued, because people sue for everything now, and they weren't giving us what they claimed. So Snickers understands this. They're a big company, and I don't know how much money they have. They probably have lots of money, but they don't want to lose it. So they're going to actually give us a little bit more than what they claim. So my theory is that they and other groups like Frito-Lay that make the bags of chips with all the air in it. They give us more than what it says on the side of the bag because they don't want to get sued. When I was a younger man, I always wanted to get the most food, the most bang for my buck, right? So I always try to, whatever gave me the most food for the least amount of money. So I like Fritos chips, because Fritos chips, I looked at the side of the bag. I can't remember how old I was or when it happened, but I just remember going to the store and all these chips were on the shelf and it said 69 cents. It had the little tag on the corner, right? It said 69 cents for a bag of chips. And I just looked at the ounces. Okay, which bag gives me the most chips? So that's what it's Fritos. Fritos gives you the most ounces for the same price. So I was like, oh, I like those for the rest of my life. And that's true. I had Fritos yesterday. Not anymore though. I'm cutting them out for a few months because of that cholesterol. Okay. Anyways, until my next doctor's visit. So I think that they give us more than what they claim. So I'm gonna change this around a little bit. So now we're gonna move on to another question. I'm not gonna rewrite the whole thing. Okay, I'm not gonna read. I'm just gonna modify this a little bit. I actually think that the candy bars that we weighed are more. I'm gonna change my hypothesis slightly here. Watch what happens to the calculation. Did the calculation change at all? Okay, the calculation didn't change because the data didn't change. Standard deviation didn't change. Sample size is still 4. Nothing changes. The only thing that changes in the entire calculation is the p-value. If I do a left tail test. If I do a left tail test, p-value is 0.96. That's the area to the left. Well, if I do a right tail test, what is this area to the right? What's the probability of being greater than 52.7? Well, this area right here is 0.96. This area down here is 0.04. Does that make sense? And we can check that. Let's do it on the calculator. We already have the information in our calculator. Go into your calculator. Stat, test, t-test, number 2. We have the data in list 1. Everything's the same except for our hypothesis, our alternative. It says not equals, it says less than, it says greater than. We're going to choose the greater than now. That's what I'm measuring is 52.7. The mean is 54.5, bigger than this value. Then I press calculate. The t is still the same. Check out the p-value. P-value changed to 0.04, didn't it? Or it's about 0.04, yeah. Okay, so we got a small p-value, small probability. The p-value is 0.04, which is less than 0.05. What does that mean? Reject HO. Reject. You got rejected, HO. That means the mean weight is greater than 52.7. I'm pretty sure based on these 4 candy bars, sample size is way too small. But based on this, I can make the conclusion, and sometimes in the conclusion, we can include our errors. So I rejected, could be a type 1 error. I could have made a mistake because we only had 4 candy bars. I'm concluding that the candy bars actually weigh more than 52.7 grams. Based on 4 candy bars, there's millions of Snickers candy bars out there, right? They're cranking them out every day, making Snickers candy bars. Now there's all kinds of flavors and they're putting all kinds of things in candy bars. But the regular candy bar probably weigh more. Okay, they don't want to get sued. I could do a 2-tail test. I could do it equals and not equals. Do they weigh exactly 52.7? Equals. So it could be, is 54.5 different than 52.7? Or is it equals? So anything in here between 0.025, anything in here is equals 53, 53.1, 54. 54.1. Okay, then we're getting out here 54.5. That's unusual. So I could actually work this out and find the exact value that is considered unusual. When my p-value is 0.05, that would be my unusual value. Pretty good. Should we weigh the king size candy bars? Or does that make sense? Let's weigh the king size and see if they give us more or less or equal to what they claim on the king size. I'm pretty sure we'll come up with the same result. So if you want to come up with your king size candy bars, so you can eat them, unless you already ate them. Again, I take donations. Oh yeah, I'm on a diet. I forgot. I can't eat a Snickers candy bar tonight. You gotta give it away. 96. Good. 96 and 96. I think we had 3 of them. You 96 also? Okay. Wow, consistency. And the other, we had 3 of them. Oh, and I don't even know how much they weigh. What does it say on the side? Okay, so that's where we're at. We're at 93.3 now. Okay, the average weight of 3 candy bars is 96. The mean weight is 96. Is 96 bigger than 93.3? Yeah, probably. I don't need to do calculations to figure that out. But I can do the T calculation, 96 minus 93.3. Calculate standard deviation. Oh, by the way, the standard deviation is 0. There's no spread there. So I wouldn't even be able to calculate this if the standard deviation is 0. Sample size, again, is too small. One of the most obvious generalizations that's out there in the world today is Subway sandwiches is the biggest chain, fast food chain that's considered fast food. Biggest fast food chain in the world now. They overtook McDonald's. And they had the most craftiest advertising campaign ever in the history of the world. Their sample size was 1. This guy named Jared lost 100 pounds eating Subway every day. So they made a commercial about it. He lost weight eating, he lost 100 pounds because he went Subway every day and ate a 6-inch turkey sandwich. Did he lose weight because he ate a 6-inch turkey sandwich every day? If I did this with 1,000 people, do you think they would all lose weight? Probably not. So the sample size is 1. So sample size is really important. Sample size is really important when it comes to calculating your T. So again, our sample size is really small. Maybe I should tell my doctor I'm going to go do that. The problem is most people go to Subway and you go to Subway, you get bacon on your thing and you put all kinds of sauces all over it, mayonnaise and all this other good stuff. Meatball sandwiches, 1,200 calories for a 6-inch stuff. So people go to Subway, but they don't order, what you should order, the stuff with the least amount of calories, I guess. Anyways, that's a T calculation. Hopefully it made a little bit of sense to you. I really like one example in here. Again, I don't refer to the examples too often. And the difference between a standard deviation is known, that's Z. We know this number, we're going to do a Z test. We don't know this number. We take sample standard deviation, we're going to do a T test. So again, one example from 7.3. I do this now because I got a hot tub in my backyard. I saved for about 3 years and I have to measure the pH in there all the time. So it makes sense to me. The pH of the water. My brother worked for a company called Ecolab. They go to restaurants, they measure the pH and the acidity of the water when they're washing dishes. An industrial company claims that the mean pH level of the water of a nearby river is 6.8. You select 39 water samples and find the pH of each. The sample mean and standard deviation are 6.7 and 0.35. Is there enough evidence to reject the company's claim? Okay, so again, this is page 381, example 5. We're gonna do this like we did before. Page 381, example 5. I want you to read through it. We'll do it on our calculator. I'll talk about it in a few minutes, but just try to read through it for like 5 minutes and then we'll go over it. There was a question online, somebody had asked, is the claim always the HA? So when you write your hypothesis statement, you have your HO and your HA, the claim, if you see more than or less than, that's the most common test that you'll run into. So more than, less than, not equals, that is when the claim is in the HA. So that happens most of the time, but it's not an always case scenario, okay? So you can't say, oh, the claim is always the HA. That's not always the case. Okay, sometimes it could be up here. And if you read through in the examples, again, I mentioned this earlier, my argument with my statistics expert. You cannot reject the claim, and in our textbook, when you read examples, they always make that statement in the conclusion. I like to stick to this. I don't have anything about the claim in the conclusion, because the claim is not always the alternative hypothesis. There is not enough evidence at the 5% level to reject the claim. Okay, I just try to avoid that situation because not always will the claim, we're not rejecting claims, we're rejecting HO. So if the claim is up here and you say there's not enough evidence to reject the claim, then you're assuming there's not enough evidence of HA, which is confusing. What I just said was confusing, but that's what kind of the book alludes to in a lot of their interpretations.
So most of the questions that's not enough evidence.
Right, so if your p-value is bigger than 0.05, not enough evidence. So several of the questions do have that. I would say, and that's not an always case as well. Like a lot of my quiz questions, you're going to end up rejecting the null hypothesis, right? There is going to be evidence on a lot of questions, because why would we do a statistical test unless we think there is a difference? Like this 16.9 ounces of water. If I think it's 16.9 ounces of water and all these water bottles in a case of water, I'm probably not going to do a statistical test. If I'm suspicious of something, then I'm going to do a test, right? Then I'm going to do a statistical test. So if you're suspicious about something, there's usually some evidence of that suspicion. So usually an alternative will have your claim, and usually you'll be rejecting, but it's not an always case scenario. Any questions on 7.3? All right. So we're on 7.4. I already put some notes on the board. This is the shortest section in the book. 3 pages. 3 pages. Most sections are about 7 or 8 pages. This was 3. And what is it? It's testing for proportions. The guidelines changed slightly because they ask you to they added now the guidelines. There's 8 guidelines, but the formula for a statistical test for proportions, you have to check conditions, just like a Z interval for proportions. The interval for proportions, you check n times p and n times q is greater than 5, just to make sure your sample size is large enough. If your sample size is too small, then your Z calculation will not be statistically significant. So I put it right here. And someone had asked about the quiz, right? This is a quiz. Number 8 is tomorrow. We're going to have 3 questions. One question is going to be a Z test. You're going to give a population standard deviation. One question is going to be a T test for means. So you're going to get sample standard deviation. And one question will be a Z test for proportions. This is 7.4. And there's formula right there. Again, it's on page 388. Z test for proportions. They give you a Q. Whenever you see Q, that's 1 minus P. Just like from before. So I'm going to collect some data and I'm going to test that data. I'm going to do a left tail or right tail or a two-tail test. There's only 2 examples in this entire section. But again, like most things that we're doing, we're becoming more reliant on the calculator. The calculator is very useful when we're testing. If I could do the test on the calculator, why not? Okay, and that's what I like to say to students. If you're in the field and you're collecting some statistics or doing some data analysis, you get a calculator, your boss is going to be like, oh, you can't use a calculator today because I said so. All right, that's never happens. So we get to use calculator, we might as well use it. There's a z-test for proportions, and I wrote the language for that z-test right here. It's called a 1-prop z-test. Later on in chapter 8, we'll learn about 2-prop z-tests. We'll compare 2 proportions. All right, so let's collect some data. We're gonna get a p hat, and we need a p. Remember, p hat is x divided by n. This is called a sample proportion. P hat is sample proportion. So I'm going to take a sample and I'm going to compare that number to overall. So I take a number and compare it to the population value. Then I can make some kind of conclusion. So I need my online people to help me out here because I'm going to collect some data. I want to know if you work, if you have a job, okay? So I want to compare that to a population proportion. So it's a yes, no question. So according to Google, I found that about 40% of people have a job. 40% of college students work. Okay. Probably this class might be a little bit higher. This is a night class, so I suspect that many of you work during the day, come to class at night. Okay, I did a lot of that myself. So I'm going to write a hypothesis statement. So I need a question. 40% of college students work. I looked it up. There's 2020 statistics nationwide. I suspect that more students that take night class work. It's going to be greater than 40%. Does that make sense? All right. So that's my hypothesis. And I use P for proportion. Notice that's a population proportion. I suppose that more than 40% of night school students work. So that's going to be my question. So I'm in step 1. And I will phrase it as a question. Do more than 40% of night school students work? College. So again, I need my online people to help me out. Just say yes or no if you have a job and go to school. All right, getting my responses online. So raise your hand if you have a job in this room. Oh, let's see here, because I looked at full-time students. Raise your hand if you're a full-time student. Okay, so I have part-time students, so this might not work. Okay, so most of us are part-time students. So there's 2 different percentages. Full-time students, about 40% of students that are full-time work. And in part-time students, that means you're not taking a full load. It's kind of hard in summer. It said 70%. 70% of part-time students work. Does that make sense? So I'm gonna just modify this to a 70%. just for the sake of presenting this information. I should have clarified that in the beginning. So we think more than 70% of part-time students work. So again, raise your hand. So I can get a count if you have a job. So I got 17 out of 20. So P hat. So on step 2, I'm going to do my calculation. P hat is 17 out of 20. Which is that's 65, no 85. 25. So that's what we're comparing. Is 0.85 greater than 0.7? One of the things we also need to do in step 2 is we need to check the condition. Oh, I forgot to finish off my HO. So I'm going to calculate my N times P be greater than or equal to 5, N times 1 minus P has to be greater than or equal to 5. Okay, so there's a difference here. Notice that in a confidence interval, when you calculate the standard error for a proportion, in confidence intervals, we used P hat because that's the only information we had. The same thing when you're checking conditions in a Z test for proportions, you're going to use P, not P hat. So this is not a hat. Okay, so I need to do the 0.7. So N is 20. 20 times 0.7 is 14, which is greater than or equal to 5. And then 20 times 0.3, which is Q, is 6, which is greater than or equal to, ooh, we barely made it. I knew it was going to be close because we had a small sample size. 20 is a very small sample. If you're comparing this value to a population. So there's condition check. Conditions will become a little more important, especially if you take another stats class. I teach another stats class and I use a different program, and condition checking is a 3-step process. One of the steps is a 4-step process. They have conditions is really important. You got to make sure you got a random sample of people. Like this was not a random sample, so I can't really generalize these results for all of Hancock College. I would need a random sample of college students. Then I'm going to calculate my Z and my P value. My Z score is right here. P hat. I'm going to write it out. 0.85 minus 0.7. Again, that's the calculation by hand. But we can do that on the calculator. The calculator is very short compared to what we did with the Z test and a T test. Again, it's called a 1-prop Z test. So let's find it on our calculator. Stat test, and this is a number 5. 1-prop Z test. So P0, 0.7. Oh, and it asks for X and N. I wrote it right up here. X is on top, N is on bottom in our proportion. Sometimes that's not given to us. We have to find it by doing the N times P. So I have to do this calculation. X is 17, N is 20. Not equals, less than, greater than. I'm going to choose greater. Is 0.85 greater than 0.7? Right now, before I do the calculation, before I find the Z score and the P value, I'm thinking 0.85 is that's probably more. I think more students in this class work than the population, which is 0.7. Does that make sense? I think we have more people that are employed. Z-score, 0.1, 0.46. And I assume that if you do this calculation, you get a 1.46. P-value, 0.07. Oh, I was wrong. Is 0.85 greater than 0.7? Are we going to reject or fail to reject at 5% level? Which one is it? Is the p-value less than, is that less than 0.05 or is that bigger than 0.05? There we go, greater, bigger. So what am I going to do? P-value is greater than 0.05. I'm on step 3. Got you. I'm going to fail to reject. Again, you don't have to write it. I used to be a stickler and be like, hey, you didn't write the p-value, you got it wrong. But the p-value is right there. I just wrote it right above. So as long as you cite that. Again, you could use rejection regions if you want. Okay, so I got my rejection decision. I said fail to reject. I got why I failed to reject, and the why is here. And now I'm ready to answer the question. I failed to reject. Okay, I didn't have enough evidence of this. Not enough evidence. The proportion of people, the proportion of students that work in the sample is greater than 0.7. And why did that happen? That's a type 2 error. When you fail to reject, that's type 2 error. I could have made a mistake.
Someone's in trouble.
And stop at stop sign. That's, I think, most things that happen around here. See people quote are not stopping. We could have made an error. It's a type 2 error. If you fail to reject, that's a type 2 error. Our sample size was really small. That divided by 20 gives us more margin of error, more error. So 0.85 is 0.85 bigger than 0.7? Okay, not really. Although there is some evidence, that's really close, 0.05, isn't it? So in a statistical world, they would say, oh, you know what, there's some evidence, there's a difference. There's some evidence that we have more people working. 17 out of 20, that's a lot. That's 85% of the class has a job. Okay. That's why I would make the deadline 11:59 p.m. because I know you're working. Okay? And family and cooking dinner and all that other good stuff that you gotta do. Right. So a lot going on. There's some evidence that there's a difference, but not enough. Okay, we draw the line at 0.05. At the 10% level, I would reject. Okay, that's why this is called alpha. You get increased alpha. If you increase alpha, you decrease your chances of making a type 1 error. Okay. If you increase alpha to 0.1 or 10%, I decrease my chance of making a type 1 error. I don't know, those guys took off pretty fast. Everyone's going that way. So maybe I should lock the door. We unlock that? Hope not. They didn't say anything. We'll stick around for a few minutes. Don't go anywhere unless you're a looky loo. You want to go see what's going on.